Okay, very good. So, okay, welcome back, everyone. Do you have any questions? No. Okay, so let's start then. I think I want to do section 4.6. So this is directional derivatives. And gradient. So especially this concept, gradient, is very, very important. And we have to understand why. So part of understanding comes through understanding directional derivatives. Right. Okay. So imagine you have a function of two variables, f of x and y, and so we define partial derivatives for this function, right? So we define fx like at a point 0, y 0. This was limit of as h goes to 0, f of x0 plus h y0 minus f of x0 y0 divided by h as h goes to 0, right? So as we emphasized, what is this quantity? I mean, this quantity is rate of change of f along the line, sorry, that's parallel to the x-axis, but that passes through this point. So you look at this point, so this is x0, y0, right? This point is x0 plus h and y0. And we looked at the values of function at this point and that point, and we subtracted and we took the limit. So that is this partial derivative in the x direction, right? That's what it is. And of course, similarly, we have partial derivative in the y direction, which is partial y of f and so on. So, okay, and same for fy. But now we want to generalize this. Do you know how we can possibly generalize this concept? In mathematics, it's always a good idea. If you're given a concept, you try to generalize it. How can you generalize this concept? Possibly. We looked at this direction, and we looked at that direction. So we got two quantities which are so important, partial derivatives, right? And how can you generalize this concept now? Well, I mean, a possible generalization would be, instead of looking at this direction or that direction, let's look at an arbitrary direction. Okay? Like u. Doesn't matter. And then what we want to do, we want to study the rate of change of f as you approach this point along this direction u. Right? So then, so this would, I just write general case. We just pick a unit vector u, right? So let u be equal to a and b. Because it's a unit vector, so a2 plus b2 is equal to 1. And what we'll do, we just look at the rate of change of this function as you approach this point along this line. So what does that mean? Is that we define this limit So this is now limit as h goes to 0, f of x0 plus ah, y0 plus bh minus f of x0, y0, again divided by h. So what we are doing, we are looking at, of course, this is x0, y0, but this point, coordinates of this point is x0 plus ha, because u is equal to vector ab, right? And this is y0 plus h times b, right? I mean, this point has coordinates x0, y0 plus h times this unit vector u, which is AB, right? H times u, which is x0, y0 plus, well, as we have HA and HB, right? That's what we have. Now, if this limit exists, then we call it the directional derivative of f at that point, right? So, if limit exists, call it directional derivative. So that's the concept of the day, if you want. Derivative of this function f at the point x0, y0 in the direction of u. So you have to specify all this direction. Of course, u we know is just AB, right? So notation for this then is the following. So notation in this case is DFU. Of course, if you want to specify the point x0, y0, where the derivative is taken, we just say DFU at x0, y0. But if you understand that you are at that point, you don't have to write it. You can just say DFU. But you understand that this is always also with respect to a point x0, y0, or xy in general. So that's the thing. Now, okay, so you see, this can be a useful concept because, I mean, what is so special about these two lines? I mean, these two lines are just two lines among infinitely many lines you can approach the point. And that's the property of the plane, that there are many, many lines you can approach a point, unlike a one-dimensional situation where basically you have two directions, either from right or from left. And in that case, you have two concepts, right derivative, left derivative. So this is a generalization of the concept of right derivative, left derivative. It's a directional derivative. It makes sense, right? We have generalized a concept from one variable calculus to multi-variable. Now, if it was just the original definition to go through, this would be difficult to compute. Okay, so difficult to compute from first principles. You see, partial derivative was not difficult to compute from first principles because we froze one variable, we took derivative respective. So this was just kids play, right? This was easy. And then the other way around, right? So that's what we did. But here, you see something, it looks like something more subtle is going on because, you know, you have to look at this point and think, how can I do that? I mean, but what comes to save us or saves the day is the following result. So we have this proposition, but we have a proposition which is absolutely crucial and a lifesaver, in this case, really, because you see that if you know partial derivatives, you can calculate this one too. You don't have to know anything extra. So is that if partial derivatives exists near x0, y0. Now, I'm not very precise about formulating this exactly, what kind of conditions we need. I just say, just rather vaguely like that, because we don't need that exact formulation really. If partial derivatives exist near x0, then you have a formula, you have an absolutely beautiful formula for directional derivatives. So the formula is this. So let me write it here. df u is equal to df dx times a plus df dy times b. Where what is a and b? A and b are the original vector u equal to ab, right? That's what. Where u was our original unit vector. This is the direction vector, right? So this is quite useful because it just means that if you can calculate partial derivatives, then you can calculate derivatives in any direction. So that's really valuable. So how can we prove this? So let me give a sketch of proof to you. What we can do, we can just form a function defined as, say, f of h. This is capital F. That one is small f. Remember, right? That's the f of h equal to f of x0 plus ha and y0 plus hp, right? So we had a function of two variables. We turned it into a function of one variable now, h, because x0, y0, a and b are frozen, but h can change, right? So that's a function of one variable. Now, according to our definition, which unfortunately I erased, f prime of 0 was really just directional derivative of f in the direction u at point x0, y0, right? Because if you just write down the definition of f prime at 0, you notice that you're going to get the same fraction, quotient fraction, difference fraction, I mean, of the original definition, right? So f prime of 0 is equal to that. Okay, so all we have to do now is to make sure that we know how to differentiate this function. So this is, of course, exactly what chain rule is designed to do for us. We have a function of two variables. We replace each variable by a function of one variable. We get a function of one variable. And now we have to compute the derivative of this. So chain rule strikes. It just tells us what is the derivative of this guy. Now I can just write it. Yeah, f prime of h. Can you tell me what is f prime of h? Is partial f with respect to x times this one. So this is partial f partial x times a partial of this guy, x0 plus HA with respect to H, plus a partial of F, partial Y, times a partial of the other factor, Y0 plus HB, divided by H. Right? You see that. Okay, now this is very easy because what is this partial derivative, for example? What is x0 plus HA divided by, with respect to H? Well, this is a linear function in H. So its partial with respect to H is just A, right? Is equal to A. And by the same token, this partial also is equal to B. Okay, so we are done now because now I can say that, okay, so then a prime of H at H equal to 0 now is equal to df dx at x0, y0 times A plus df dy at x0, y0 times B. Now we just write this in a simple form as we just write it in a simple form as f sub x A plus f sub y B. And of course, this is equal to start with, you see, derivative is this partial directional derivative is equal to B F U. I don't write x0, y0 because that's kind of cumbersome to write all those things, clutters, notation, my notation. So that's. Any questions so far? Oh, there is a question in the chat. I'm sorry. Maybe it's already answered. No. Does that mean that the FU is U dotted with the gradient? Absolutely, that's what it means. Yeah, indeed. I'm going to say that exactly. Exactly. Thank you. Yeah, exactly. Very good. Right. So now I can write it as dot product of two vectors. One vector is fx, fy. The other one is ab, right? So this just means that then directional derivative. So I'm now writing from left. Directional derivative, this is equal to fx, fy dot ab, right? Now, this quantity has got its own name because it appears in all these calculations. It is a kind of very important character in all this game. It's called gradient. So this is called gradient of f dot u, where gradient of f, which is inverted triangle. Don't write as a triangle. If you write as a triangle, what does that mean? You know what it means, right? Sorry? Change. Triangle? No. What is this notation? Have you seen this operator before? The delta. Delta, yeah. Well, what does it signify?
Isn't it the non-infinitesimal change?
Which one? This one?
Yeah, big delta.
Maybe in some contexts you have used that, but we are going to say that this is actually the Laplacian, the Laplace operator. We defined Laplacian before, but maybe I didn't give a notation for that. But this is the notation of Laplacian. Anyhow, we don't have to know that right now. It's not essential. I'm just emphasizing that don't use the inverted triangle. Don't confuse the inverted triangle with the triangle. This is an inverted triangle, and that's the gradient. Okay, so that's gradient. So, but what is it? This is just a vector, which is fx and fy. So it's a vector that has its components are partial derivatives of f with respect to x and y. That's it. It looks like we have done nothing. You know, you can say, okay, I know what partial derivative is. So what's the point of it? There's a lot of points about introducing this notation. I mean, one of them, the first one for us is just this very, very interesting formula, right? Directional derivative is the dot product. Okay, so we are good there. Okay, so now let's use this formula to do just one example calculation, and then we'll see what we can do with it. Because there's a lot that now you can do with this concept. Gradient. Okay, so here's an example. Compute fu at 0, 1 if f of x and y is equal to x2 log of 1 plus y2. Yeah, okay, that's it. And of course, u is the unit vector that makes the angle of pi over 3 with the x-axis. Right? Go to unit vector with angle theta equal to pi over 3 with a positive x-axis. Okay, so I have given you the unit vector like that. I've given you the function, and I've given you the point, right? So we want to compute this function. Okay, first of all, let's see what u is. I mean, if you draw, this line is making the angle theta equal to pi over 3. So pi over 3 is 60 degrees, so it's closer to 90. So I should respect the angles at least a little bit as much as I can. So that's theta equal to pi over 3. But mind you that this is a unit vector, right? So u equal to a and b. Now you have to understand what is a and what is b. Can you tell me what is a and b? Yeah, of course, exactly. This is a, this is b. So a is equal to 1 cosine of theta, right, that angle. And b is equal to, well, I mean, 1 cosine of this angle, which is the complementary to that, so it's 1 sine of theta. And why did I use 1? Because it has length 1. The vector has length. So this is equal to cosine of pi over 3, which is, what is cosine of pi over 3? That's a 60 degree, right? That's, do you remember what is it?
1 over 2.
Sorry?
Is it
1 over 2, yeah, that's sine of 30 degree, which is 1 over 2, so that's 1 over 2. And what is b? So sine of pi over 3, which is root 3 over 2, because root 3 is the square root of 1 minus a quarter. So yeah, I think that's correct. Right, so that's cool. And now what we have to do, we have to compute these partial derivatives. Okay, we'll do it. What is f sub x? a partial derivative of this guy with respect to x. That's 2x log of 1 plus y2. But we are interested at the point 1 and 0, right? So, sorry, 0 and 1. So that point is just x0, so this is 0. That's nice. What is fy? This guy with respect to y is x2 times 2y divided 1 plus y2. But again, unfortunately, x is 0, so this is also 0. This was not by design or out of my laziness, believe me. If anything, it was just by mistake. I just picked the easiest answers, but I'm lucky. Okay, so that's 0. Okay, now we have, but still, I mean, we have to write the formula, which is something. So dfu is equal to gradient of f times u. So gradient of f is equal to fx fy is equal to 0, 0. So that's 0 vector, 0. Okay, but not 0 number, 0 vector, right? So that's a 0. Okay, so then this is equal to 0 dot u. And it turned out that if we started the problem from the other direction, we didn't even have to compute this unit vector. Okay, so that sometimes happens in calculations, so that's good. So that's equal to 0. But this 0 now is a 0 number, and this 0 is a 0 vector. So that's it. Okay, so now you can do questions like this, but still there is something lacking here, namely we still want to understand the meaning of this gradient in a deeper, in a better way. I mean, okay, so that's good. It helps us to measure rate of change in different directions. But now we are interested in knowing in which direction the function changes maximum possible, and which direction it changes the minimum possible, and in which directions function basically locally, infinitesimally, I would say, doesn't change. So this is the kind of question we want to answer. So any questions before I move into that topic? Looks like there are no questions. Okay. So now, so the next topic is that in which directions it's a question. So in which direction function changes by a maximum or minimum amount? That's the question. You want to answer this question now? Right? So there is a condition. So let's assume we are not in this case. So assume that gradient of f at x0, y0, which is partial derivative, right? fx of y at x0, y0. This is from 0. This is different from 0. So let's assume that that vector is not 0 vector. What does that mean? It means that at least one of these factors, components of the vector, is not 0. That's what it means. Okay, good. Now we can answer this question fully. Then 1. The function changes in maximum possible amount in the direction maximum amount in the unit direction along this vector gradient of f. And second, f changes by a minimum amount it's going to be negative actually in this case along minus mind you there is a minus sign gradient of by that amount. So we have to prove these two statements. If you prove one, you can prove two, and vice versa. So they're really proofs are quite parallel. So let's see why this this is true. So proof. So rate of change along u, of course, this was directional derivative, right? But we notice that this is just a dot product of gradient with u, right? This is now all that now. So this is a non-zero vector, right? This vector, I just assume that we are in this case that that vector is non-zero. Now, can you tell me for which u this is going to be maximum, and for which u this is going to be minimum, and for which u this is going to be zero, for example? So for which u this vector is going to be, this number is going to be maximized, right? We know that this number is equal to length of f, gradient of f. So this is equal to length of gradient of f, length of u times cosine of theta, right? So this is, of course, different from 0, but this is equal to 1. So being maximum or minimum just depends on cosine of theta taking its max or min values, right? And for that, we know that theta equal to 0 is maximum rate of change. Okay, so then u is equal to gradient of f divided by its length. Okay, now I'm all of a sudden writing 1 bar. So you're allowed to write 1 bar or 2 bar. I used to write 2 bars, so I just keep same style still. So because after the break, I tended to forget everything that I did. So I have to remember now what we did. All right, so u is equal to gradient of f divided by the. Okay, so that so 1 is done. Okay, so that's. And the maximum, the minimum value of the dot product is when the other vector is making angle pi with that, right? It means that in the other direction. So that 2 now is very easy also. Similarly. IEU is going to be negative gradient of f divided by this one. We'll get negative rate of change, which is actually least. Actually, this is not just least, it's actually negative. So this implies 2. So So that's the second case. But now you can also ask, well, I mean, everything was done under the hypothesis that gradient is different from zero. But you should now ask me, what if the gradient is zero? If the gradient is zero, what happens? Yeah, the function, yeah, all directional derivatives are zero. So let me put it like this. So that's an important case. So let me write it here. If gradient is zero, that's the third case, the gradient of f at x0, y0 is equal to 0, then dfu is equal to 0 for all u's. What does that mean? It means that if you move along any direction and you study a function along these different directions, you're always going to get 0. So rate of change is 0. But does it mean that the function is constant? This function that infinitesimally up to first order terms doesn't change, but there might be higher order terms that change it. Right? So I have to warn you that this does not mean that the function is constant. So f need not be constant. Of course, a good example now, that example that I did now serves me well because the example I picked right at the beginning is an example of such a situation. We had a function whose gradient at one point was 0, but that function was totally non-zero function. We had x2 times ln of y2 plus 1. That's a non-zero function. So that's the case. Okay. Now, but you might ask, okay, so the function changes maximum amount in this direction, but what is the maximum rate of change itself? You see, there are two issues. We have function changing by maximum amount in this direction, but now we want to know what is the maximum rate of change. So let me also mention this. So just complementing case 1. Maximum rate of change is equal to, of course, df du is equal to gradient of f dot u is equal to gradient of f. U, we just found that is gradient of f divided by its length, right? So this is equal to gradient of f squared over very nice, because we just showed that it's a simple calculation, but it's valuable to memorize that yes, in the direction of gradient, this is u, and this is gradient of f. The amount of change is actually given by the length of the gradient vector itself. So that's quite valuable piece of information. And similarly in case 2, if u is equal to negative. So I don't go through these things I wrote. I'm not going to write it again, so that's. But now, what if I am in a direction that's orthogonal to the gradient? In that case, of course, rate of change is 0. I'm not saying the gradient is 0. I'm just saying the direction is such that you're orthogonal to the gradient. Then the rate of change is 0. So this is kind of I would say this is case 3 prime, maybe, because case 3 was greater than 0, so case 3 prime. If U is orthogonal to gradient of F, then still, rate of change by definition, this is 0. So please remember that case also. That's a good case to remember. So here's an example. Temperature in a room is distributed by, say, T of X and Y. Well, because room is, it's a two-dimensional room, let's assume. It's not a very realistic room. In a 2D room, is distributed by T of X and Y equal to log of x2 plus y2. Well, this room actually has a puncture in it, so this kind of singularity you don't allow to approach that point. So it's so hot there, for example. It looks like it's so hot in the center that you cannot go there. But that's not so unrealistic, actually. So it's a hot area. Okay, anyhow, so temperature. So now we are asking at the point one, two, in which direction, or the point is fixed, in which direction temperature changes by maximum amount. Okay, so what is asked here, you see, kind of have practical applications actually. I mean, hypothetically, but there are similar situations which do have practical applications. What we're saying is that there's a point 1, 2, you're at this point, and you want to know in which direction. So imagine somehow you're very cold there and you want to move into a very hot area. So which direction you should move so that you pick up maximum amount of temperature. So for example, you want to go through tropics or something, it's kind of warmer areas. In winter, maybe you want to escape there. So kind of 1, 2. So in which direction we should go? Well, according to this, we have to compute the gradient of F. What is gradient of F? Gradient of F is, T, sorry. Gradient of temperature is Tx dy. Well, that's equal to ln u, u prime over u. This is 2x over x2 plus y2. 2y over x2 plus y2. And we want to know in which direction we have to move, right? So u has got to be equal to gradient of t divided by length of gradient of t. So if you compute this vector at the point 1 and 2, right, you're going to get this vector, right? So this is 1, 2 over 5 and 4 over 5 divided by length of this vector, 2 over 5, 4 over 5, right? We computed gradient. This is Tx, Ty. This is correct. And U is the maximum rate of change, is obtained along this line. Okay, so 2 over 5, 4 over 5. And we have to compute this number. That's not bad. So what is this guy? This is 1 over 5 times the square root of 2, 4, and 16, 20. That's it, times the 2 over 5, 4 over 5. So this is equal to 1 over 25 square root of 20 times 2 and 4. Actually, you can simplify this further because there is a 2 and then you can factorize here over 4. But that doesn't matter. This is good enough. That's the direction. So you see, there is something not very satisfying in this problem because this function why it's not satisfying? No, this is perfect. Do you find anything wrong with this?
I don't think the center for this harbor is too cold.
The center for this thing is too cold? Yeah, that's right. This is actually minus infinite temperature, right? It's like a black hole, but it's not a black hole. It's very hot, very cold. So you're right, cold. Such temperature doesn't even exist because temperature cannot go below negative 273. That's a 0 Kelvin, right? Which I still don't understand why it should be like that, but that's, well, I understand, but I don't know why, well, anyhow, so that's a different story. Okay, guys, do you have any questions? Okay, so you guys have a good day, and I see you on Wednesday. Thank you. So I just stopped the recording.